Reworking the foundations of a computational complexity. Perhaps the single most profound fact that has been uncovered by computer science so far is the ubiquity of computational intractability. Literally, thousands of natural problems have now been shown to be NP-complete or worse. If we had to describe the situation in a picture, it might be figure 1.2, which shows the situation for a generic computational problem pi. The input to pi is x, and the figure depicts the apparently inevitable combinatorial explosion, since as usual pi is NP-complete or worse. The formal setup of a classical computational complexity theory can be uniquely sketched as follows. First of all, to keep things simple, the theory is about computational problems which receive an input x about which a yes-no question is asked. The input is described as a string over some convenient fixed alphabet. If we let sigma star denote the set of all possible strings over this alphabet, let L pi, which is a subset equals to sigma star, denote the set of all strings x that described an input for which the answer is yes. Then we have the formal foundation of a classical complexity in language recognition. Given the input x, the problem is to determine whether x is in L pi, that is, whether x belongs to the language of yes instance of the problem. The question is then whether there is an efficient algorithm to recognize the strings that belong to the language L pi. The problem is that the answer is generally no. Among the bad news uncovered in the first decades of computer science is that for many natural problems pi, the language L pi cannot be recognized by any algorithm, and that for thousands of other innocuous seeming problems, polynomial time recognition algorithms for L pi probably do not exist. The bad news concerning the ubiquity of computational intractability continues to deepen. One of the most profound developments of the 1990s, based on new and sophisticated algebraic methods, has been a host of results showing that most of the NP hard problems that can be formulated as optimization problems also probably do not have good approximation algorithms. What is a practical scientist to do?